Hello everyone, my name is
서영옥.
from KAIST. Today I will be presenting Force Control, hand ray casting with user-defined pinch force for control display gain application. In many XR applications today, users interact with small, densely packed 3D targets. For example, in CAD environments or data visualization. Hand ray casting is one of the most natural and widely used pointing techniques for these scenarios, especially because it does not require a handheld device. However, hand ray casting has well-known limitations. It is constrained by human motor accuracy and hand tracking noise, and its precision degrades with distance. Prior work has addressed this through target-specific approaches, such as expanding selection volumes, hierarchical disambiguation, or object rating systems, but these depend on known target layouts or additional devices. Our goal is to improve pointing precision in a way that is both target agnostic and bare hand. Here is the key idea. Force control adds precision modes on top of standard hand ray casting. The ray behaves normally until the user exerts pinch force. At that point, the system applies control display gain to dampen the ray's movement and improve accuracy. Our interaction system addresses two challenges. First, how to activate precision modes, how to switch between normal and precise ray casting, using a bare hand modality. And second, how to enhance the precision of the ray casting itself, how to geometrically modify the ray in a target-agnostic way. Let me walk through each of these. We will cover these two pillars in order. For the first challenge, activating precision modes, we need a bare hand input modality. Our approach is to use pinch force, measured with a surface electromyography armband worn on the forearm so the user's hand remains completely free. The key challenge here is individual differences. People vary widely in muscle strength and force perception. Our contribution is to use user-defined pinch force, where each user subjectively determines their own force levels. Specifically, users define their input force intensity using the Borg scale, a well-established subjective scale from 0 to 10. In a preliminary study with 12 participants, we validated that users can consistently exert the same pinch force at a given Borg scale level. The relationship between the Borg scale and percent of maximum voluntary contraction was linear. We selected two force levels: moderate, corresponding to level 3, and very strong, corresponding to level 7. These levels are reliably discernible to users and produce stable SEMG signals. The classification pipeline uses an 8-channel SEMG armband, a CNN classifier, and a history accumulator for robust real-time classification. Now let me show the interaction states. Force control has 4 states. In the coarse states, the system works like standard ray casting: coarse pointing when the hand is open, and coarse dragging when the user pinches without force. In the precise states, pinch force activates the CD gain. Moderate force triggers precise pointing, where the ray's movement is damped, and very strong force triggers precise dragging, allowing the user to select or manipulate objects with high precision. The state transitions are designed for robustness. When the system detects a pinch, it waits about 50 milliseconds for the force classification result. If force is none, it enters coarse dragging. If moderate, precise pointing. Precise dragging is only reachable from coarse dragging or precise pointing. We assume users do not change precision and initiate a click simultaneously. Releasing the pinch always returns to coarse pointing. The state is also locked for 0.6 seconds after each change to prevent jitter from rapid classification fluctuations. Now, let me move to the second pillar, enhancing the precision of ray casting. For the second challenge, we modify the ray's geometry to improve precision. The key requirement is that this must be target agnostic. It should work for both selection and placement. The main challenge is that CD gain is ambiguous in 3D ray casting, since the ray extends infinitely. Our contribution is a set of CD gain application strategies specifically designed for 3D ray casting. In 2D pointing, the CD ratio is straightforward. It is the ratio between mouse movement and cursor movement, since the control and display spaces are obvious. But a 3D ray extends infinitely and lacks a fixed cursor, so there is no clear definition of CD ratio. To address this, we propose three strategies, each applying CD gain to a different component of the ray formulation. This figure illustrates the three strategies. Let me explain each one. CD hand pose is the most straightforward approach. It treats the real hand as the control input and a virtual hand as the display output. Both the hand's displacement and the change in ray direction are scaled by the CD gain, and the ray is extrapolated from the virtual hand position, which is not rendered. This effectively creates a virtual hand that moves slower than the real hand. The trade-off, however, is that the ray can visually detach from the user's physical hand, which can feel disconcerting. CD Ray Deer takes a different approach. It keeps the hand position as is and only scales the change in ray direction. This preserves visual continuity. The ray stays aligned with the physical hand, which users found natural and intuitive. The divergence of the ray is moderated compared to baseline, but resolution still drops with distance since the ray keeps diverging. CD Ray Rev is our most novel strategy. It scales and reverses the directional change so the ray converges over time. You can think of it as the hand being the control, and the resulting movement of an imaginary target along the ray being the display. Because the ray converges, precision actually increases with distance, the opposite of standard ray casting. This makes CD Ray Rev particularly effective for high-precision tasks. We conducted a user study with 16 participants, all intermediate to expert hand ray casting users. The study included two tasks: a selection task, where participants picked a target from among densely packed spheres, and a placement task, where participants precisely aligned a sphere inside a cube. We tested 4 technique conditions: baseline, CD hand pose, CD Ray Deer, and CD Ray Rev, each at 2 depth conditions. The CD gains were set so that angular resolution at 2 meters supports targeting objects of approximately 1 degree. Here is a summary of how the strategies compare. CD hand pose can cause the ray to detach from the hand. It was less preferred because the participants felt their arm heavy. CD Ray Deer keeps the ray aligned with the hand and is best suited for selection tasks with moderate precision demands. CD Ray Rev causes the ray to converge and is best for placement and high-precision tasks. It was the most preferred technique for difficult conditions. Compared to baseline, all 3 force control techniques significantly reduce selection errors, with p-values less than 0.001. All 3 techniques also significantly reduce placement jitter, again with p-values at or below 0.001. Perceived performance on the NASA Task Load Index was significantly enhanced with all force control techniques compared to baseline. Beyond these numbers, there are 3 important implications. First, user-defined force was feasible. Participants successfully controlled the system with only a one-time calibration. Second, the benefits of enhanced accuracy clearly outweighed the effort of force exertion. No significant increase in perceived physical workload was observed. And third, ray convergence, CD Ray Rev, works best for high-difficulty tasks. Users described it as natural and intuitive, reporting significantly less jitter and better perceived control, especially at greater distances. To conclude, we propose force control with 2 main contributions: user-defined pinch force to activate precision modes, and CD gain application strategies to enhance pointing precision. Compared to standard ray casting, force control reduces selection errors, placement jitter, and frustration, especially for small and distant targets. Among the 3 strategies, CD Ray Rev with ray convergence is most effective for high-difficulty tasks. For future work, we plan to explore more stable force sensing, continuous CD gain mapping, real-time force feedback, and real-world use cases. Thank you for your attention.